So we're recording. We had a pre-lecture due today and homework. We're going to talk about MRAM. It's a little bit, this is not quite what I do in the lab, because believe it or not, what we do in the lab is I use MRAM and ReRAM, but we don't use them to remember anything. We use them in weird states they were not originally designed to be used in. This is why Crossbar went out and designed us our own custom ReRAM chip, so I didn't have to hack into it. Everspin was kind enough to give us some of their test modes and test codes so that we can hack into the chip knowledgeably. Okay. But we will talk about some basic technology between of the two. These are actually commercially available now. They just don't have as large a format. And the MRAM chips we bought are 16 megabytes, or 16 megabits, I should say. So nothing really large scale, but they still have niche applications because they have a lot of superior qualities. A week from today, Dr. Cambo is going to come in and talk. I did post his 380 lecture on MOSFETs to your BB Learn shell if you're interested. It's where the technology's at now. So if you're going for a job in the semiconductor industry, it's a really good resource for you. And he's going to talk about memories in this class, mostly MRAM and ReRAM. Probably not talk about not using them as memories though. And I'm not talking about not using them as memories either. After that, we go into CMOS imagers. That's the last new topic, AKA what Julie did for a living. And there's a final exam. So it's mostly a story of, I know how all this got developed because I was there.
I brought you five for the backflip.
What?
The backflip.
The backflip?
No, we're the joke. We're not, it's not matter. It's, oh, are we going to have a backflip?
Okay. So this slide evolved a couple of years ago. It was my cunning plan to get out of doing ABET for the summer.
First day. But now you're students, you don't have to worry.
Well, it was the first year I worked full-time in the lab, so they couldn't ask me to do anything I didn't want to do. All I have to do is say, talk to my boss. But yeah, so I'm going to grad school, and that will be more work I want to do. And then I'll only be teaching 2 classes next fall. So this is from a book by Rainier Wasser, and it's kind of like the update to the C book, which was the classic of semiconductor device physics for years and years, and what Daphne Chen is using in EE490. And this is just more, it's more geared towards the technology today, and less geared towards a learning textbook. So I went through the MRAM and the ReRAM sections of them and read them carefully and developed these slides, and also from what I know in the lab. MRAM is commercially available. It's not a research fantasy. One of the big companies producing it is somebody called Everspin Technologies. They're in Chandler, over down by whatchamacallit, that other company, Intel. And it's yet another Motorola spinoff. One of what you learned about in the pre-lecture quiz was you read an app note, and those app notes are really good sources of information, and all companies have them. And if you're looking for more information on a particular device or a particular topic, it's a great resource.
It was nice that it had a lot of information without like an overload jargon.
Yes, because they're gearing it more towards people who are learning about it. TI and especially analog devices are really good. Analog devices has amazing applications engineers. And if you want to learn about something like, how do I collect data using an ADC? What are my signal considerations on the input? Go to them. And they have tutorials written for this stuff. And it's a good place to get started. And just always go to the manufacturer's information. And they're always willing to help you out, especially if you're going to buy their products. Especially if you're going to buy large quantities of their products. They will help you out on a personal basis, send out an engineer to talk to you or whatever. What? You read the last bullet point on my slide. So basically what was in that app note was talking about for SSDs, a lot of people use DRAM to temporarily store data that needs to be read out faster. You want to read out data in bursts, or you want to write data in bursts to the flash. You don't want to wait the read and write lag times on the flash, so you write it directly into DRAM and then write it into flash at your leisure, or read it from flash at your leisure and send it out in a burst. If your data is critical and you're worried about power going down to the DRAM, meaning lost data, maybe you're executing stock trades, and if you lose that data, millions of dollars have just been lost. You want to have backup power for your DRAM to keep it from going down. Now, the big advantage for MRAM, if I put an MRAM in place of DRAM in this burst data write little mode, MRAM does not require backup power. And backup power is big, bulky, and expensive. It usually involves batteries or super caps or something like that. So the cost of the MRAM is comparable to the cost of the DRAM plus the batteries. And it helps give people another set of reassurance on these high-end SSDs that their data is not going to be lost. So they've really found a niche here, and they can use that to improve the technology and get money, so they can improve the technology and get larger format memories, and then that will help it become more mainstream. Yes, and Crocus does make MRAM too, but we're not going to talk more. We just don't talk about them. Do you know why we don't talk about Crocus? Okay, good.
You haven't ever told us that Canva is not talking about it.
Yeah, exactly. He's not overly fond of that company. Okay, let's put it that way. Okay. So what MRAM is, it stands for Magnetic Random Access Memories. And the way we do this is with something called a magnetic tunnel junction, and we'll talk about the physics of that today. They use a MOSFET to select which MRAM cell is actually selected. So it's a 1T, 1M structure, kind of like the DRAM was a 1T, 1C, same type of thing. And we're going to store the information in how the magnetic field is oriented in the MTJ relative to a reference device. They really had an opportunity here. When I first looked at these devices, I knew the name of them. And unfortunately, I didn't get to name them because I would have called it a flux capacitor. It doesn't take a 1.21 gigawatts though. But the spintronics, and if you listen to Dr. Cambo's lecture from 380, he talked about that as a technology for the future for mainstream computing, but right now it's a technology of now for these MRAM devices. And we want to actually be able to merge the magnetic processing with CMOS. And we'll talk about how they do that later. But basically, I have to get my CMOS devices integrated into the same chip with my magnetic devices, and it's different processing technology. So they basically just have to process it twice. Now, the way they change the magnetics is because the spin of the electron actually affects the magnetic properties of a material. If it's spin up, the magnetic field's going to be oriented in one direction. If it's spin down, it's going to be oriented in another direction. If we can change those spins, if we're capable of magnetically polarizing, making it so all the electrons are spin down and they all line up in one direction, I'm going to take those magnetic layers, and if they're matched, they're going to have a lower resistance. If they're not matched, I'm going to have a higher resistance. And the two layers are separated by a dielectric, so there's no conduction between the two of them. The only way the information is passed is through the magnetic field and through tunneling, kind of like we saw in flash. And yes, I would have called it a flux capacitor. That was just a lost opportunity.
And there's a lot, I feel like there's a lot of missed opportunities in like technical naming. Like there's so many things. This could have been so much more interesting.
In 639 last spring, Cambo was going through his lecture and going through everything and talking about these, and I just burst out, I would have called it a flux capacitor, and everybody in the class laughs, and Bertrand's looking at me like, what?
It's a him in that diagram cartoon.
He's seen these slides. Okay, so here's my quantum interlude. All quantum states and spin of an electron is a quantum state actually exist in a superposition of states. I can polarize them in one direction or another. Now, if I polarize them at a 45-degree angle and I force an experiment that says this is going to have to turn out at 0 degrees or 90 degrees, two orthogonal states, when I measure this thing at 45 degrees, there's going to be an equal probability of it coming out being 0 degrees or 90 degrees. Once you make that a measurement, the spin has shifted. It is now at, or the magnetization level is, direction has shifted. It is now at 0 degrees or 90 degrees. You forced it in that state to make the measurement. Right. And this is what I get to do next year. I shoot single photons, and they have a polarization, and there's 4 different possible states. Yes, my little single photon detector.
It hurts my brain to think about singular photons.
There's lots of photons.
It just hurts my brain to think of it.
Okay.
Just try to think of a singular photon.
Okay. So this is an MTJ. Notice our passive sign convention is going the correct way. This wasn't handled by physicists. We've got current flowing into the positive voltage terminal, and we're going to measure the resistance across it when we use it as a memory. And this is the most basic way we can do it. There's 2 layers of ferromagnetic material. There's one here and one here. There is a dielectric in between them. Notice the flux capacitor structure, magnetic, dielectric, capacitor. Okay, the dielectric has got to be thin enough. We're talking 1 to 2 nanometers, 10 to 20 atoms thick, that electrons can tunnel through. If the layer's thin enough, I can tunnel electrons through it without putting a lot of energy into it. So there will be some current flow through here if I put a high enough voltage across here. And in this case, the high enough voltage isn't like 20 volts. It's more like normal voltages like 2.2, 3.3 volts that these devices run off of. I can build these MTJs in a standard CMOS process if I have a spintronic back-end process. They can be integrated into standard CMOS electronics, but it just takes some extra processing steps. Okay, and depending upon whether I have a higher resistance, if I force current into this, if I have a higher resistance, I will get a higher voltage. A lower resistance will give me a lower voltage. If I force voltage across it, I can measure current and determine what the resistance is. This is what we do a lot of in the lab. It just comes down to V equals IR. just measure things very accurately.
Ohm's law.
What? Ohm's law, yeah. So how this works, I have two layers here. And this says the electrons in the emitter are spin polarized, and I can change the direction of the polarization in the emitter. I cannot change the direction of the polarization in the receiver. So if I have my polarization going in this direction, I magnetically polarize my electrons in this direction. When they want to tunnel across my very thin oxide here, what I'm going to get is I'm going to get a higher probability because the electrons over here are in the same state as the ones over there. So there's a higher probability that they're going to tunnel through. And if they tunnel through, it produces current. It's an electron moving. Electrons per second is another unit of current. If we have a whole bunch of them, it's coulombs per second. And more electrons tunneling through means more current, means lower resistance, or something like that. V equals IR.
Something.
Yeah. Okay. So if they are polarized, the two layers are polarized like this in orthogonal directions, I have a high resistance. If they're polarized in non-orthogonal directions and they're equal, going in the same direction, I have a lower resistance. Okay. So the electrical resistance is proportional to the relative polarization of the two layers. Now, one of the beautiful things about this is something called the resistance area product. And we can easily adjust the resistance area product by varying the thickness of the dielectric layer. As engineers, we've just gotten a handle on how big the resistance is going to be when we measure it. This can range from tenths of ohms to tenths of ohms per tenths of ohms times micrometer squared to mega ohms per micrometer squared. For CMOS, most of the resistances, as we learned in 380, come out to be in kilo ohms. So all I have to do is just vary the thickness of the layer until it's in the kilo ohm range to match it up with CMOS. And we have something that will work well with CMOS that way. So here's the tunneling effect. Yes, tunneling through the dielectric is more likely if there's an available state on the other side that matches the state of the tunneling electron. The tunneling probability is going to be, if we look at the storage layer here, it's going to be the smallest when the polarization is in this direction. The tunneling probability is going to be the highest when it matches what's on the other side. And we can vary the resistance that way. When we read it out, what we're really reading out on MRAM is the resistance of the cell that's already been programmed in there. Right. And if we apply the voltage, it's amazingly simple how you do this. We'll get to that.
Controlling tunneling.
Controlling tunneling. Well, you're controlling the magnetization. Right. So the magnetization of the reference layer is penned in a certain direction. It's going to stay that way. And the storage layer is what we're going to do. There, it seems like I have a whole lot of slides that say this. The resistance is, yeah, I just said that. Okay. Now this is the 1M, 1T cell. We have a magnetic tunneling junction, and it is going to be connected to a transistor that can be turned on or off. When we select that transistor, we're allowing current to flow, and we'll have a variable voltage up here on the output, on the bit line, depending upon what the resistance of that MTJ is. Now there's several companies doing research into this. Micron is, but they won't admit it, even to me. But I know.
They're doing it in the back room.
No, they have a secret building up there.
Secret back room building.
No, and people were amazed that we got to go into the secret building. It is the technology development building. And I don't know why, but before we went in there, there was like this coffee bar. They're all over the place at Micron. You can get free cappuccinos, mochas, whatever, you want. And like for the first time in like 2 years, I said, I really need some coffee. So I slugged back this mocha cappuccino, thing before we went in there, and they put us in the room with this guy. And this guy, it was like 2 hours of nonstop different technologies he was coming up with, just spewing out of his mouth really rapidly fast. Fortunately, I drank the coffee.
It kept you up to speed with him.
Yes.
That's their secret coffee.
Their secret coffee. So I mean, it was just it was amazing, all of the stuff that they're working on. They wouldn't admit the MRAM or the ReRAM stuff. Freescale is doing some research into this, even though they sold off the division who was most competent to do this, which is called Everspin. IBM, NEC, Toshiba, Samsung, a lot of companies are doing research into this, and Everspin is one of the first to market. The other people who have come to market, but they're not nearly advanced, is a company called Crocus, but we don't talk about them.
So, Bill, I'm just curious, why is IBM not necessarily as relevant as they used to be? Like, do they just scale back as a company? Did they slow down?
Like AT&T was in the same position. IBM had these huge research labs. They were engineering playpens. They were wonderful jobs if you could get them. I knew a guy who worked at one of them. It kind of like JPL, or my end of the lab at JPL. So it's just a big engineering playpen. And these people didn't have to chase funding, didn't have to chase proposals. All they had to do was sit back and come up with new brilliant ideas. And it was a relaxed enough environment that you could do that, and you could pursue crazy ideas. Like at JPL, there was one guy in our group. His entire research focus was blowing bubbles in space. There was a whole group of people there that wanted to build a ladder to the space station. I'm not making that up. There's people working on quantum computing and all this other stuff. There's just, random people as it struck their interest to do that. JPL has something that very few places do, and this is why a lot of people we're trying to get into there, is if you develop a technology while you're working at JPL, you're a Caltech employee, Caltech will give you 50% of the patent commissions. Yes, there's nobody else that gives you a deal like that. And this is why everyone flocks to Caltech and flocks to JPL. Oh. That's how they got Eric there. Eric Fossum. He's a you'll see him in the next set of slides, or in the Imager set of slides.
I remember Pat Kelly used to work with that.
Mm-hmm. Yeah, and it's just all that money they were throwing at research has kind of dried up and gone away. It's not as good as it used to be. Nobody has the money for that anymore.
And throw money at one goes in space.
It was a beautiful idea. No, really.
It's awesome. I'm just saying.
If you're blowing bubbles in space, there's no gravity, so the bubbles are perfectly spherical. They are the most perfect spheres you can get anywhere. Now, the reason why this is pertinent to real work is that if you have perfectly spherical membranes, you can grow optics on them that are perfect. for like these machines that Dr. Cambo talked about in his lecture in 380, where you need absolutely perfect optics to do the extreme UV optical stuff that you need to make stuff at 1 nanometer.
That is really cool.
Okay.
That's really cool.
It is, but you know, and we the first like he was Chinese, but I mean these Chinese PhDs were brilliant, but their English wasn't very good, and they would leave articles out of their proposals, and our division manager would not let the proposals out of the department until it was readable. So I was one of them I was one of the people who native English speaker who could go through and just add articles into his speech and make it make sense without changing the meaning of it. And they all love me for that. It's a skill I very seldom admit because you get stuck doing it forever.
The story of Dr. Howell actually because I want to blow bubbles in space.
Yes, and so this was the title of his proposals. I want to blow bubbles in space. I'm just laughing my head off. I'm going, okay, this is just going to be useless. But you know, then nobody funds that stuff anymore.
It's so cool though.
Yeah, and think of the practical applications of blowing bubbles in space. And also, I just have to say this. His name was Yu Wang, and that's how he answered the phone. Yes, you. We actually had a great group. It was a very diverse group, and the fact that we were about like a third of us were native-born Americans, a third were Indians, and a third were Chinese, and we all got along great. And it was amazing that just the cross-cultural diversity of ideas was a really good thing. Okay, where am I at? Okay, research devices that didn't work.
Oh boy.
This is the first attempt to make MRAM. I'm looking for something in here, but I haven't gotten it to yet. I'll get there. Basically, this is called a Stoner-Wolfarth MRAM, SW-MRAM. We have 2 orthogonal magnetic pulses applied to the device, and this is how they get programmed. And the 2 orthogonal pulses are called H-hard and H-easy. Now, when I was first reading this, I didn't understand the names, but I think I got it later on. During programming, the select transistors are off. You're just applying the magnetic pulses directly to the device. Okay, keep on going. Get through this. To program a 1, what you do is H-hard and H-easy are both positive and somewhere in this region right here. So I've got a hard axis and I've got an easy axis on this magnetic field graph. And this is called the Stoner-Wolfarth asteroid. Sorry. Right, and if I want to program a 0, I'm going to put the 2 pulses down here. And so H-hard remains positive, and H-easy becomes negative. And I think the reason why they got these names is you don't change H-hard because it's hard to change. You can change H-easy though, and that's how you're going to get to the programming. How do you generate magnetic fields inside an integrated circuit? You know, we don't normally have inductive elements in there. We're going to have to put magnetic materials in there through that back-end process. And remember that magnetic fields can be generated by running currents through wires. If I run the current in this direction, I get a magnetic field curling around it. I run it in the current in this direction, I get a magnetic field in the other direction. So that's how you can change the polarity of the magnetic field, is by changing the direction of current flow. The first time I asked Dr. Cambo this question is just, how do you get a magnetic field? He looks at me and goes, it's just Maxwell's equations. And all wires have inductance. As we learned in 490, even tiny little wires, you can calculate the inductance of them. They're like in nanohenries or something like that. Little antennas hanging off of all your little dip packages. Yes, that you didn't even see. And this is why I groan when I see people with like these loops of wire that are this long. Or,
yeah, and then like I miss like days where like Sharber would actually get mad at people for that kind of thing. Now,
I miss Sharber.
Yeah, I miss Sharber in general.
Yeah.
Yeah, that apparently 7 months didn't get mad at people for having.
He's a digital guy. I'm sorry. Something has been lost in the world. Today I got a phone call from this guy down in Tucson who is the VP of engineering at a company, and they do data acquisition, which is basically, when you're talking about data acquisition, you've got sensors in the real world, and you have to be able to turn that into digital data. And getting an accurate reading of what the sensor has as a whole analog art form. And he is actually plans to start hiring from NAU because he thinks we do a better job at analog than anybody else in the state, which is sad. Because our analog is me.
It's you and anyone that like took and Dave Scott.
Dave Scott, yeah. Dave Scott was a good old analog engineer. Sharber. And it's still an important field for electrical engineers. When the digital revolution came along, like in the 1990s, when we're going to do everything digitally, they thought they would never need analog engineers again. So a bunch of analog engineers trained as digital engineers, but they were really good digital engineers because they understood the analog electronics behind what they were doing, and the new digital engineers don't. Yeah. And so they kept it going for a while. Now the demand for analog engineers since that time has actually increased, but it hasn't increased as fast as the demand for digital engineers. But there's fewer people actually teaching this stuff. So if you have some skills, it's a good skill to advertise and to use.
It's actually kind of a good thing that like Alex Dahlman kind of still keeps the freshmen in line with having them not have giant wires. As much, but he can't catch all of them.
Right. And power people are good analog engineers too. I've come to accept that. I would have never said that when I was an undergrad.
Yeah, actually, yeah, because
they do DC to DC converters and things like that.
Your master's a power engineer.
Yes, and he understands controls theory and things like feedback and things like that. And why did it fail? Pretty much it had a really high power consumption. And scalability, it was hard to make devices smaller. As you made the devices smaller, the power per unit area went up, which was not a good thing. So this is devices that are actually being sold. And we're going to talk about Everspin's technology here. Okay, so where Everspin came from. The idea of toggle MRAM was developed at Motorola. And this was, I believe it was actually in the group that Dr. Cambo was working at the time. So he's like, he either knows or he was in on the original development of MRAM. Then Motorola got split up into this very serious, like large number of kingdoms that it is now. And one of those was called Freescale. And Freescale decided to spin off their MRAM operations into a company called Everspin. And they are down in Chandler, and they are very Motorola. And they're manufacturing MRAM from about 256 kbits to 16 megabits. They maybe have larger formats now. The 16 megabits is the ones we're actually using in the lab. Applications, a flash replacement. It has higher speed than flash, and it has higher endurance than flash. It doesn't break down as much. So if I'm doing data logging and I want the data in there really quickly, and I can't have it be volatile, file allocation tables, anything that I want that's just a really reliable, but I can't store a huge amount of data, only 16 megabits. Now, if you look at the range of these applications, you're going to start to see some of the things, reasons why why everybody wants this to work. Not only is it durable and non-volatile like flash, SRAM, this is the fastest memory we have. But it's volatile. The speeds on this are comparable, and will be in the future very close to SRAM, faster than DRAM. Battery backed up systems where critical data need to be stored quickly on power failure. So I can download everything that's in the SRAM into MRAM. As the power goes down, just have a battery to keep it up for a little bit of time and download it all into MRAM, and I haven't lost my data. It's a lot of vias. Oh yeah, we'll talk about those vias in a minute. Space applications. It's naturally radiation hard. Anytime you put memory in a satellite, it is a train wreck. Space radiation. High energy particles coming in can completely obliterate whole sections of your DRAM. Flash isn't quite as bad. Completely obliterate SRAM and permanently damage DRAM. What they have to do in order to use these memories in space is they back them up. And for every bit you write, you have to write it twice or 3 times, depending upon how critical it is. They shield it. They have to put it in a big, heavy metal cage. And this big, heavy metal cage, and when you talk about when you're launching something on a satellite, one of the big contributors to cost is weight, because you have to have 3 times as much fuel as 3 times as much fuel as you have for the added weight of the device. So if you add like 1 pound of shielding, you need 3 more pounds of fuel to get it up there. So this is a great application here. ReRAM is also rad hard, and we're about ready. We're going to prove that.
ReRAM, the RAM, Lord of the RAM.
Lord of the RAM. Oh, that's the last slide. Okay. Now, if you look at this processing structure, down here, I have, looks like a standard CMOS structure. I've got a transistor, or probably have an NMOS transistor. I have a word line, I have a drain, the source, I've got the substrate, probably a FET now or something like that. And I want to put the MRAM on there. What I'm going to have to do is I build a stack of vias and metal going up to give me some mechanical spacing up here. So, and then I put a big metal core stud up here. It's 4 layers of metal up. So I've got, you know, good micrometer, so distance up on top of it. And then I take this thing that I have produced on a standard CMOS line, and I give it to another foundry that's going to put the magnetic materials on there and process that. So this is a single MRAM cell, is this orange area right here. And it's vertically relatively tall, but it fits in the same size as a single transistor. Okay. So this toggle RAM is one of the types of MRAM that Freescale or Everspin is selling. Right, and I just said that. Uses a standard CMOS process to build up the front. They call this the front end process. Everything below that line is the CMOS front end. Everything above that line is the back end magnetic processing. A little bit more expensive to process, adds to the cost of the MRAM, and one of the reasons why, another reason why, other than cost, that it's not used everywhere. The circuitry is connected with a big stack of vias. So we've established that. Okay, the scalability problems with toggle NRAM. As far as they've been able to get with this is about the magic number I've been talking about a lot, 16 megabits. I need to keep the energy difference between the two states high in order to guarantee that the data lasts 10 years. 10 years is the magic number. You want to know why 10 years is the magic number? Because flash lasts 10 years.
Fair enough.
Okay.
Understand?
Okay, so they want it to be as good as flash. And I have to keep, I'm going to have a high energy difference. This high energy difference is going to mean I have to switch high magnetic fields, and it increases the switching of these as the devices grow smaller. So I still have to have the high magnetic fields in a smaller area. The Webers per nanometer square get to be astronomical compared to the Webers per micrometer squared if they're in a smaller area. And there is a natural limit on how much current we can put in there to induce these magnetic fields. And this is called the electromigration limit. And it's exactly what it sounds like. It's when the ions start moving. And if you think about ions moving, it means atoms are moving. And when atoms move, they go in the place where they're not supposed to be. And when you've got a 1 to 2 nanometer thick tunnel oxide, it's only 10 atoms thick. If I lose a couple of atoms and they splat out in the wrong place, they can cause shorts, they can cause, opens, and they can damage the device. And they're really not expecting anything below 45 nanometers. So we can't scale it down, is the basic thing. Now this says research devices for future production. And this was when I first wrote these slides about 2 years ago. It's present production now. When we went down to Everspin, it was me and Bertrand and this guy from France. He was the dean of some college in France. It was like the oldest university.
Is it Campo's teacher?
No, it was just somebody he knew. But it's like the oldest college in the universe or something like that. Maybe not in the universe, but at least on, at least on the oldest college is still operating on the planet.
Because I know Oxford University has been around since the 1100s.
It's older than Oxford.
Wow. Okay.
But there's some argument about that, because it's like, well, it was closed down for some years during the plague or something like that. I don't know. Okay. Useless information. But we went down to Everspin, and they were really surprised that I had heard about the spin transfer torque, because they were just starting to do it. But I was reading the Rainier Wasser book is where I got my information from. And besides, I was just who are you at all this? Wait, I'm down there with Bertrand and the Grand Poobah. It's like, who are you in all this? I'm the memories teacher. But I know about this. Okay. So Everspin is starting to produce these now. It's called spin transfer torque, and STT-RAM is the acronym for this, not flux capacitor. It just rolls off your tongue. What I want to do here is, when I have two states in here, when I'm writing a 0, I'm going to have I've got my pin layer down here, and then I have my storage layer. So this is my pin layer. It's going to stay fixed no matter what. I'm going to put VDD, look at how beautiful this is, a VDD up here and 0 volts right here. And when I do, it's going to force the current to go through in one direction and force the magnetic field orientation to be in that direction. If I want to write a 1, I simply change the direction of current flow. And how magically do I do that? I put 0 on the top and I put VDD on the bottom. It's easy to do. All I have to do is switch which one's going on. Yeah, I just put the direction of the current. And my magnetic polarization is now in the other direction. So I have the difference between a 0 and a 1 right there. And this is called spin transfer torque. It's switching the magnetization instead of putting a magnetic field in. So switching the direction of magnetization takes far less energy. We'll have numbers for that in a minute. All I have to do is switch the voltage polarity. Okay, how much current do you need? Okay, the first thing I got out of the Rayner-Wasser book was it's 2 mega amps per centimeter squared, and that number terrified me. And then I started playing around with units and converting it. Well, how much is that per micrometer squared? I'm expecting this to be a huge number. Well, per micrometer squared, that comes out to be 20 milliamps per micrometer squared. Now I'm starting to get a much warmer feeling about this. And if I go down to nanometer levels, it's only like 20 nanoamps. And that's for 10 nanosecond writes. This is comparable in speed to DRAM at these relatively low current densities. So now I'm getting something I can use. The total current required goes down as the size of the cell goes down, instead of goes up as the size of the cell goes down. And again, we can help. They're thinking this will go down about to 45 nanometers.
2 mega amps is a pretty scary.
Yeah, especially 2 mega amps in a centimeter squared. That sounds huge.
It's horrifying.
It is. I'm thinking of like lightning bolts and a little tiny like lightning bolts and something the size of a dime.
Instead of flux capacitor, it was Zeus RAM.
Zeus RAM, yes. That would be the other one, the Stoner Wolfram. Okay. So one of this way, we want to try to scale this down. And one of the ways we can do this is let the material scientists at it. And this is what they come up with. They have all these different layers of materials that make it just right, which complicates the processing, which brings the cost up. Yeah, but if I can get it down to 20 nanometers, I may have something that's a direct DRAM replacement. Now notice I've talked about MRAM as being a flash replacement, I've talked about it as being an SRAM replacement, and I've talked about it as being a DRAM replacement. This is a pretty powerful technology if we can get, again, the densities up. We need more than 16 megabytes. How many movies can you store in 16 megabytes? 0. How many?
Really short.
It's a short movie, yeah.
Really short movie.
Okay, now here's the next breakthrough we've got. Where there is current, there is heat. The heat losses from current can be calculated by this amazing formula called I squared R. It's a really good one to remember. Since I have current, I'm going to use the heat. As I run the current through it, I heat the device up, and I'm going to look for materials that will change their magnetization easier when they're hot. And there's a whole class of materials like that, fortunately. And this is called thermally assisted MRAM. So we talked about the spin transfer torque as something for the future that is happening now. The next step, and I happen to know Everspin's working on this, is a thermally assisted MRAM, and maybe I could combine the two. So this thermally assisted, basically I'm going to temporarily heat the junction very locally using electrical current. And then after it's warmed up, I'm going to apply a magnetic field or use spin transfer torque at the same time. Now, the material they pick is chosen so that the magnetic field needed to change it decreases with temperature up to about 200 degrees C. It's getting pretty warm in there. It's not that you can't touch the device. The package is cool, but this one particular cell is really hot for a short amount of time. Because it's only one cell, it can dissipate that heat throughout the whole package. And H is the heating current. And if you look at this, and I know when Bertrand comes in here with slides, there are going to be all kinds of hysteresis curves. So let's just talk about these real quick. This is the whole, and with the whole idea of hysteresis, I've talked about it before too. Somewhere, was it 490? Yeah, or maybe this class, I don't know. But anyways, the idea is as I program it, it's going to stay in its low state. It takes a higher H field to flip it into its high state than my normal operation. Now, if it's already in its high state, it's going to take putting an even lower H field in there before it flips. So if I read it in between here and here, it's not going to flip it. I can just read the resistance without flipping it by putting it in between there. If we use this for digital circuits, well, probably 280 or 380 yeah, Schmidt trigger inverters. They're beautiful.
Yeah, I mean, we did in other 490.
Yeah.
Some more Schmidt trigger stuff.
Yeah, yeah, and I do that in my other secret class. What?
Other secret class.
My other secret class. It's all analog.
Fifth floor and the fourth floor, the fifth floor and the 4-story Micron building?
It's the 5th floor and the 4-story Micron building, my secret class. The last person who's I've allowed to take the secret class was Corey, because he needed it. Yeah, and he was someone who could do it and really understand. I think Heather Melville, there's been a few. It was originally written for DJ at Gore, because he just wanted more analog.
That wasn't 490 last semester.
No, it was what 490 last semester evolved out of. But there's a whole nother layer of this. It's a lot deeper, and it's more analog. Okay, so this is thermally assisted TAMRAM. The magnetization of the storage layer is switched when the device is warm. So I first apply a heating current and let the device warm up. How long does that take? 3 to 5 nanoseconds. Okay, way faster than flash. Not as fast as SRAM. Once it's warm, I put a relatively weak pulse of magnetic field by probably adding more current to it, and it's generated by a pulse of current in the bit line. And remember, the all wires are inductors rant from embedded, probably right next to the grounding rant. The heating current pulse is also induces a magnetic field. We pay attention to the polarity of that pulse current, and that's what decides whether it's going to be switching it up or switching it down. It takes about 10 to 20 nanoseconds for this to cool down once it's heated up. So the total write cycle's about 30 nanoseconds. It's a little slower than DRAM, but yeah, okay. Where can we take this? We have 2 good ideas. We have spin transfer torque. We have the thermally assisted. We can put them all together and have TASSTT, thermally assisted spin transfer torque. We combine those 2 ideas for better performance. We have there's some processing issues with it yet, and I don't think Everspin is doing this yet in production. They've talked about it a little bit. And there is problems with electrical breakdown just because of all those mega amps per centimeter squared. And it's good, it lasts for about 10 to the 12th cycles, but to be comparable with flash, we need to get it up to about 10 to the 16th cycles. So what have we got here? God, we get out early today. We have the potential, you got to see the slide. Okay, we have the
It's pretty good.
we have the MRAM potential. What can it be? If it has the density of DRAM, if I can get enough cells in a small enough space, I can use it for programming memory. They're starting to talk, some of these modes, they're starting to talk about we can push the speed of SRAM. You can use it for cache. And the non-volatility of flash, we can use it in SSDs. If we could only get past 16 megabits, we've got the one memory to rule them all, the holy grail of memories.
ReRAM can be that.
Well, ReRAM has that same potential too.
Okay, so it's either MRAM or ReRAM.
Or it's whichever, yeah, whichever one gets there first. I think ultimately MRAM is going to be a little bit more expensive. Well, it is, because you have that whole magnetic backend processing. But when we start to get down to true single atom transistors, we need something that's going to be like a spin up, spin down kind of thing. The spintronics may take over as we get down to like some smaller sizes. But I think in the short term, ReRAM wins. I think MRAM is still a technology for 10 years in the future.
I think the only thing that made this slide better is you just had a proto holding, they just Photoshop in out the ring and have proto holding like a
Memory chip.
Yeah.
Okay, so any questions? You guys have been quiet all day except for Ben, and I'm just glad Ben's here. Because when Ben's the only one in the classroom, but when Ben leaves, it's like I'm in here talking to myself. I feel silly. Let's see, who do I have that I'm still looking for? Richard, Nolan, and Shujian. I'll go through the list.
It was actually relatively talkative on Tuesday when I wasn't here.
Yeah. So Zach fills in with Ben when Ben's not here. No, I just don't see anybody here. But next Thursday, I would like to say this. I know most of you are in town because you showed up for the exam. Next Thursday, Dr. Cambo will be here. And I know it really kind of picked him up a little bit to be in 380 with 5 people in the classroom, and all 5 of them were asking questions.
Yeah.
And they were asking some really good questions too.
Because when he came last semester for 380, I'm pretty sure I came to that.
Yes.
One too, even though I wasn't in 380.
Right. So if you guys just show up on next Thursday, it would make me really happy. There may be bonus points involved if you actually show up in person, or if you ask questions in chat or something like that, or just talk and ask questions. So he's going to be talking about MRAM and ReRAM and making transistors small. So it's been a long year for all of us living in the very quiet bubble. Okay, no questions, so I'm going to stop recording. Okay, and I will see you.